Okay, so there is 4:15, so we are back. So I would be happy if you turn on your camera. Okay, and so we finished with defining this FD hierarchy. And now let's do a final task in this sequence. So previous task was to find a finite vase with tower size of reachability set. And now I want to make a third task with even bigger size of reachability set. So this task is the following. I want a vase to have, so let it be a D vase, D-dimensional vase, and has size at least.
Excuse me, we can't see what you're writing.
Okay, thank you. Yes, I should share, but fortunately I haven't written down a lot. So task 3 now is the following. Find a D-dimensional vase with finite but at least around fd-1 size of the reachability set. So as before, we have defined 4-dimensional vase with tower, so F3 size of the reachability set. Now I would like to generalize this to dimension D. So actually, if you have an idea now, tell immediately, and if not, just a few minutes for thinking. But as soon as you know how to do it, just tell me.
How about iterating this construction for additional, even further coordinates, like 5th, 6th, and so on?
Exactly. Yeah, exactly. We want to iterate this construction. So the question is how to iterate this construction. So I will copy the construction for 4 dimensions. I will try to add the 5th dimension, and the rest will just say and further as similarly. But let's see whether we can actually iterate it. Right. We should be able to do it. So how do we add the 5th dimension to get F4? So F4, to recall, it's iteration of tower n times. Okay, so we iterate taking towers n times. So this is one tower. So how do we do it? Okay, we can think a bit how to change it into something like F4. So I will do a first step. So add zeros in all the existing transitions. Maybe we'll change it, but at the moment I add 0. Okay. And probably we should add some state here. So some ideas. How should we make it? Okay, I give you a moment to think. Okay, so what do you think? So are there some problems with? And probably natural move would be to add here to take the 5th coordinate to be counting how many times we have done tower. Yes, so this is probably intuitive. So the 5th coordinate, so the outer loop between P and S should count how many times we have towered. So this should be 0, 0, 0, 0, minus 1. Here we should have probably some loop which moves something from somewhere to somewhere. And there should be a coming back loop, maybe adding something. It's not clear, yeah? So let's do some try. So what should be moved in the loop in S?
So from third to fourth, analogously to previous states, I guess.
Probably, yeah. Let's try this. From third to fourth. So does it make sense? So in the previous case, here we had this tower on the third coordinate. So okay, so it looks good. So we have a big value on the third coordinate. So now we should move it to a fourth one, because fourth one counts how many times we we can exponentiate. So like first iteration would be we make a tower on third one, and we want to move this tower to the fourth one, because now this would be the number of exponentiations which we allow for ourselves. So this looks reasonable, yes? But we move it from third to fourth. And now when coming back, what should happen here? And I guess that probably if we write 1, 0, 0, 0, 0, this will probably work. But I'm not entirely sure about details. So how would it look like? We have started before from what? 1, 0, 1, 1. So maybe we should start from, I don't know, 1, 0, 1, 1, n. And then we reach what? 1, 0, and here tower of size 1, so probably 2, 0, n. Okay, so maybe it's not so important, like all the details about that. I guess that that you see that this fifth coordinate can work as counting number of iterations of previous function. And if we make it, if we manage to fix all the details of this previous stuff, we will actually be able to tower exactly this number of times as the original value of fifth coordinate. Do you agree that maybe not exactly that gadget, probably that gadget will work, but maybe would add a bit too much? So who agrees that this computes something like F4, maybe +1 on the chat, or some questions? I would be happy to answer. Okay, so roughly speaking, you agree. So only 5 +1s. Should I consider this as the other people are not so sure about that? So if you have any doubts, please. I think that it always improves the lecture if you ask some question, or if you say, "Yeah, I'm not sure about that." Okay, so I assume that this is roughly speaking fine. So in that way, you can see, or you can kind of believe, that if we have d-dimensional vase, we can produce vase which have enormous reachability set. but still finite. So this gives you, I think, a feeling that you can do very weird things here. So maybe one comment. So why this does not give a lower bound on reachability problem? Because it looks, I mean, if you have huge reachability sets, then also, so if you have such a divas, such that if you start from S, you have very huge reachability set, then definitely there are some points here such that this path is very long. Also around this FD minus 1. So what about designing, for example, a vase in which if you have a target T and source T, then every path from S to T has length FD or something similar. So we would like to, so it would be natural to design something like that, but here you have such a gadget, and then you have here a similar gadget, but maybe working the other way around. Yeah, and here, only very high, you have some jumps from this, let's say X, this is Y. Yeah. So what I draw here is maybe some naive approach to constructing vases in which, if there is a path from S to T, then this path is very long. You know, you do you do some big stuff here and here, similar as we have constructed, and we allow for jumps from this point to this point. But the point is that this doesn't work. So you can do such things, but then if you want to go from S to T, you can also go somewhere very close, jump here, and come back here. And this construction, I can't say cannot be used to construct vases in which you have only long runs, but it's not clear how to use it, and probably it's not possible without some smart constructions. Of course, if we construct a vase, so maybe some remark about path, length of paths. So usually, the usual approach to reachability is the following. Kind of a small property is proved. So if there is a path from S to T, then there is a short, with different meaning of short, path. So this is how in many cases reachability is solved. Many cases, I mean, for example, for two-dimensional vase, or also in general case, it's kind of, or in some subclasses, or in the case of coverability problem, about which I will tell you later. So this is why I give you this example of vase. So first step to construct vases which are hard to solve is to construct vases in which you only have long paths from source to target. Because if you would, for example, know that for every source and target such that target is reachable from source, you always have some path which is exponential length, then you can just search through all such paths, and you have algorithm which is not too long, not actually in p-space. So if you think about showing that reachability problem is hard, you should be able to design vases which have only long paths between sources and target. But this was maybe a digression to give you some intuition for the future. And now we go into well-quasi-ordered technique, which I promised you it will show you how to decide reachability for vases with finite reachability set. But that was, of course, quite stupid, because if you know that a vase has finite reachability set, just by using brute force, you compute it by adding and adding new reachable configurations, and at some point you see that this set stabilized, and therefore you cannot do more. But this is not a problem for my talk. So the technique which I would like to present you is much stronger. So I was thinking during the break a bit about this, and I will show you by this technique not only that for vases with finite reachability set you can compute this reachability set, but that you can decide whether reachability is finite. And this is not so trivial, because this brute force technique doesn't work. You cannot just compute what can you reach, because if your set gets bigger and bigger and bigger, you never know whether it's infinite or maybe it's very, very big, but you still haven't reached this size. Okay, but we will start from some general remarks about about quasi-orders. So quasi-orders. So first definition. Okay, so maybe what is a quasi-order? It's something similar as to an order, but you don't have a condition about antisymmetry. So you may have elements such that x is smaller than y and y is smaller than x, but still x is different than y. So quasi-order, this is reflexivity and transitivity. But this is not really important here. So we say that quasi-order x and such. I think I will move it further. Is a well quasi-order commonly we will shorten it as WQO. In Polish we say WQO. If maybe this should go further to right. If, first of all, so there are two conditions. There is no infinite descending chain in this quasi-order, and there is no infinite anti-chain in this. So maybe I should make a comment. So usually, actually, in I think all of the cases which I have seen, we apply this to orders. So, definition uses name quasi-order. So this is why I define it for quasi-order. But I think I always think about an order here. And so please don't ask me, I'm not prepared to answer the question is, what is actually infinite anti-chain in the case of quasi-order? Maybe there are some subtle stuff. There is some subtle stuff there. Think about that X and that this is an order. And then infinite descending chain, just to recall, to be sure, it's an infinite sequence of elements such that every next element is smaller than the previous one. And anti-chain is a set of elements which are incomparable. Okay, so well quasi-order. So it's not, so maybe disclaimer, well quasi-order is not a quasi-order which is well. So so being well ordered is not containing infinite descending chain. So a quasi-order which is well, it fulfills the first condition, but it doesn't necessarily fulfill the second condition of having no infinite anti-chain. So there is a clash of names, unfortunately, but just keep it in mind, these two conditions. So using these well quasi-orders, it's a very useful technique in infinite state systems. And usually it's useful to show that some algorithm terminates. And it's useful to have equivalent formulations of this well quasi-order. So I will formulate this as a lemma. So it's often that that people define differently this well quasi-order as another equivalent condition. So, but I decided to define it like that. And there is a lemma that for any order, I will just write order because I don't care about quasi-orders which are not orders. The following conditions are equivalent. So first condition is definition, yes? So no anti-chain, so no infinite descending chain, no anti-chain, no infinite anti-chain. Second condition is the following. In every, a completely different flavor, but it will be much more useful in bounding algorithms. In every infinite sequence, x1, x2, x3, etc., of elements of x, there is a what we call dominating pair, domination. Yeah, so this is like definition on the fly. What I mean by domination, there exist two indices, I and j, yeah, natural numbers, such that xi, so the ith element of the sequence, is smaller in this order which we consider from xj. So element which is farther is bigger than element which is previous to this element. Okay, and condition 3 is a similar style. So first line is the same in every infinite sequence of elements of x, but there is an infinite sequence of dominations. So what do we mean by that? So there exists indices I1 smaller than I2, smaller than I3, etc., such that element on the index I1 is smaller than element on the index I2, is smaller than element on the index I3, etc. So there is an infinite, say, growing sequence. It doesn't have to be growing. Sometimes it can be in next element can be, so can be the same as previous one. For example, constant sequence is also okay in this respect. But you not only have one domination somewhere in the sequence, but you have a domination followed by domination, 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 and so on. So this will be very useful. So now proof of that. So I have promised half an hour of exercises, but I think it will make sense if I prolong a bit this lecture part, and then there will be a natural point for exercises. I hope this is okay with you. So proof of that. So two implications here are very easy. So first of all, implication from 3 to 2 is trivial. So if we know that we have a set X with order such that in every infinite sequence there is a sequence of domination, so then there is in particular also one domination there. Yeah? So this is completely trivial. So this is obvious. Implication from 2 to 1 is also easy. So if you know that in every infinite sequence there's a domination, then I claim you cannot have infinite anti-chain and you cannot have infinite descending chain. Why? Because imagine you would have infinite anti-chain. Then you write in this infinite anti-chain as a sequence, and there is no domination there because everything is incompatible with everything, yes? So infinite anti-chain would imply no domination. But also infinite descending chain also implies, so you write this element as a sequence and you have no domination, because domination means element which has smaller index is dominated by something later. But this infinite anti-chain, infinite descending chain is smaller and smaller. So infinite descending chain, this also implies no domination. So if you know that in every sequence you have a domination, you cannot have infinite anti-chain and you cannot have infinite descending chain. And this finishes the proof of this implication. Yeah. So the interesting implication is implication which closes the cycle of implications. So from 1 to 3. Yeah? So if you have from 3 to 1, from 2 to 1, and from 1 to 3, then you finalize proof of this lemma. And I will prove it by, so you have probably different techniques of proving this, but I will prove it by a theorem which I think is of independent interest, and you use it in various fields of automata theory and maybe also in other places. So this is why I think it's interesting to prove it here, to state it here and to prove and to use it. It's theorem, maybe you have seen this. It's called infinite Ramsey theorem. And I also believe this is a most elegant way to prove this. And so you probably know Ramsey numbers, and they are connected with stuff like you have a clique of big size and you have a bunch of colors and you color edges by this by these colors, and you want to have some monochromatic click. So this is for finite graphs, and this is also what infinite Ramsey theorem talks about. So it's formulated like that. But actually, proof is easier than in finite cases. Every infinite graph, which is a clique, so infinite clique with edges colored, on some finitely many colors, on finitely many colors, contains, as a subgraph, but I will not write it, contains an infinite monochromatic clique. Monochromatic clique. So what do I mean by monochromatic? All edges are of the same color. Yeah, so you color here edges. So in monochromatic clique would be all the edges have the same color. All the edges have the same color. Okay, so let's prove of Ramsey theorem. Let's prove it. Okay, so imagine you have this infinite clique, and we list vertices. We order somehow vertices of this clique: v1, v2, v3, v4, and so on. And we look at the first vertex. So there are many edges outgoing out of this vertex to different vertices. Clique is infinite, so infinitely many edges, but finitely many colors. So there need to be some color such that there are infinitely many edges of that color outgoing out of V1. Let's say it's red, yes? Maybe it doesn't go, maybe red goes here. I don't know, red goes there, to V7, and so on, infinitely many of that. Okay, so this is our first step. And we start ignoring these vertices, which such that from V1, there is an edge which is not red. So we ignore V3, we ignore V6, and so on. So, so now we look at the subgraph of V1 and all the vertices such that they are connected by a red edge to V1, okay? So, but I don't want to draw a complicated picture here. Okay, so maybe it's okay. So now I look at the second vertex, it's V1, V2, and I look on all the other vertices to the right, which are, let's say, active. So such that they are connected by a red to V1. So now, there is infinitely many vertices, but finitely many colors. So some color occurs infinitely many times. Maybe this is different color. Maybe this is a green one. So V2 is connected, let's say, with V4 by green, with V5 by green, maybe with, I don't know, maybe with V7 as well, but with some other guys not, yeah. So we proceed further. So now we ignore vertices which are not green connected to V2, and now we look at at V4. I will do this story one more time. So now we look at edges from outgoing from V4 to something to the right, and there is some color such that there are infinitely many edges of that color. Let's say blue. And we do it, we proceed like that further to the right. Every vertex which survived, like the iterations of the previous vertices, we apply this, this system to this vertex. So if we go like that, after, let's say, infinitely many iterations, you you filter this graph and you get such a still infinite graph, such that for every vertex, all the edges are going to the right are of the same color. So you may, sorry. So you may hesitate whether maybe if we do all these iterations, maybe graph will become finite because we have done infinitely many phases of filtering, maybe somehow graph gets finite. But observe that this is not the case because after every finite, so how to argue about that? So for every natural number n, this graph which remained at the end is bigger than n. Yeah, because you can apply first n iterations, and after first n iterations, graph is still infinite. And if you have, and then you will never remove these n vertices which you have created. Yes. So indeed, after these infinitely many iterations, your graph will be infinite. And now, I guess, so now every vertex has its color, like this vertex before. Its color is blue. So, okay, it's connected with green to V2 and with red to V1, but it's with blue to everything to the right. And now there are infinitely many vertices, and everyone has a color coming from finitely many colors. So there needs to be a color such that there are infinitely many vertices of that color. Let's say blue. And then we know that every blue vertex is connected with every other blue vertex by a blue edge, because every edge, let's say between these, I don't know, V20 and V30, for V20, this edge is to the right of it, so it's connected by blue. And here we have an infinite sequence of vertices, which is a blue clique, monochromatic clique, because all the edges are blue. And this finishes the proof of this infinite Ramsey theorem. Any questions about this proof? Or it's fine? Okay. So now how do we apply it to to the implication from 1 to 3? So let's recall what we wanted to prove. We wanted to prove that if our order has no descending chain and no infinite antichain, then in every sequence there is infinite subsequence of dominations. So we want to prove that in every sequence there is infinite subsequence of dominations. So let's take our sequence x1, x2, x3, x4, x5, and so on, and we want to extract an infinite subsequence of dominations. So we will now color. So this is a clique. These elements xi will be nodes, and there will be edges between them, and we will color them like that. If xi is smaller, let's say that I is bigger than j. So here is xi and here is xj. And we will color this edge somehow. If xi is smaller than xj, smaller or equal, let's say we color it blue. If xi is bigger than xj, let's say we color it red. And if xi, xj are incomparable, then we color by green. There are no other options. Yeah? either the xi is smaller, equal, or is bigger, or is incomparable. So now you color the whole this infinite clique by 3 colors. So therefore, by infinite Ramsey theorem, there is a monochromatic clique. Infinite clique. And the question is of what color? Red, blue, or green? So can the can the clique infinite monochromatic clique be green? Cannot, because green means incomparable. So this would mean no antichain. This would mean not no antichain, but this would mean infinite antichain. So we cannot have a green clique. Can it be blue? Can it be red? No, because red would mean next element is smaller. So this would mean infinite descending chain. So no option for such a clique, no option for such a clique. Therefore, our clique needs to be blue. And this means that there is an infinite sequence of dominations. Yes. So these vertices in the clique, which are connected necessarily by blue. There is some infinite clique here. And so on. Necessarily, this is smaller equal this is smaller equal this is smaller equal this, and so on. And we get an infinite growing antichain, which is a sequence of dominations. So this finishes the proof of the lemma. So now we know that these 3 conditions are equivalent. Okay, and I need to have one more. I think it's good that I prove one more lemma, and then we go to exercises, and we'll maybe start tomorrow with exercises. So I will prove a lemma. So now we would like to understand how these well quasi-orders look like. What is a well quasi-order? What is not a well quasi-order? And this will be a first lemma of that style. So I claim, and then we will go to examples, that if x with some order on x is well quasi-order, and y with some order on y is quasi-order, then its product with a product order is well quasi-order. Maybe I should define what is that. So by this I say that a pair xy is smaller in this product order from x prime y prime if x is smaller than in the x order from x prime and y is smaller in the y order from y prime. So on every coordinate, a pair needs to be smaller or equal. So this is just a product of 2. Maybe I'll shift it. So how to prove that such a product? So this is a lemma which is called Dixon's lemma. How to prove it? If we have a previous lemma, it's very easy. So we take some sequence of pairs, x1, y1, x2, y2, x3, y3, and so on. and we want to show that there is a domination here. Whatever the sequence is, there is a domination. This is a sequence of elements from X. They all belong to X times Y. So how do we proceed? So first of all, we know that X is a well quasi-order. So if we look at these elements on the first coordinate, and we consider only the first coordinate, we can extract an infinite sequence of dominations on first coordinate, and second coordinate is arbitrary. So we can extract out of that sequence x1, y1, then maybe x3, y3, x4, y4, x6, y6, and so on, infinite one, such that it's growing on this first coordinate. It's a sequence of dominations. Okay? And then, because we know that Y is a well quasi-order, so then from sequence of Y's, we can extract an infinite sequence of dominations. So then we can extract an infinite sequence. Maybe x1 is not anymore here, but x3, y3, x4, y4, maybe then, I don't know, x8, y8, and so on, such that this is an infinite sequence of dominations, and on Y, it's also an infinite sequence of dominations. Yeah, so then it means actually this is an infinite sequence of dominations with respect to the X order, this with respect to Y order. So therefore, this sequence is really a sequence of dominations in the product order. Yes. So this finishes the proof. And now we have a corollary. So maybe before a corollary, we should state some very simple fact. Natural numbers with order is a well quasi-order. So why this is true? So first of all, everything is comparable here. So there is no antichain of size 2, so also no infinite antichain. And when there is no infinite descending chain, if you start from some number, let's say 9, then you can go down only 8 times. Yeah, from 9 you can go to 8, 6, 5, to at some point you will get stopped. So there is no infinite descending chain. And therefore, corollary of Dixon, which is sometimes also called Dickson Lemma, Dickson's lemma. Sometimes this general fact is called Dickson's lemma, sometimes this one is called Dickson's lemma, is that for any dimension d tuples of natural numbers with order, this is coordinate-wise order, is a well quasi-order. And this, how do you prove this corollary? You can say by induction, yes? For n equals 1, this follows from fact. And from, if you know that this holds for d, you multiply, yeah, so proof, induction of d, for d equals 1, this is the well quasi-order, and for d equals -1, yeah, step from d to d plus 1. So we know that this is a well quasi-order, and we know that this is a well quasi-order. So then, by Dickson's lemma, you know that product of them is also a well quasi-order. Yeah? So this okay. So this finishes. That proof of Dickson's lemma, and maybe now we can have exercise. Okay, exercise. So the question is, which ones are well quasi-orders? And I propose I will write many points, and everybody thinks for, let's say, 5 minutes, and then we will synchronize and discuss it. So first point is integers with normal order. Second one, where lex is lexicographic order. Now words over AB and also lexicographic order. Natural numbers with divisibility relation. So A divides B relation. Then words over finite alphabet with prefix relation. Okay, maybe this for now, and we will probably, this is okay. This is enough for today, and I will continue with that tomorrow. So let's think for a few minutes. Which are well quasi-orders? And if you have any question about which order is what, please ask. Maybe some cases are already done. So have you solved some of them? Okay, so maybe you can tell which ones are done and why.
First one is easy, I believe. Because we can have like a sequence 0, -1, -2, -3, and so on. It is descending and infinite.
Exactly. First one is easy. It's not true, and the point is descending chain. Okay. Have you done something more?
So the second one should be a WQO.
Why?
So it's a total order, so there are like no anti-chains, no, like every two elements are comparable to each other.
Exactly.
And there cannot also be like infinitely long descending chains. And like it's a bit messy, but you can, like, if you take the first, like assuming, let's assume that such chain exists and it starts with some element, like say AB. And so the only thing that this sequence can do is it can decrease B sometime, like a few times, and it decreases till it becomes something at least 0. So it can do at most B steps, and then it has to decrease the first coordinate by something. And so it changes it to like A-1 or A-2 2 or anything like that. But as soon as it changes to a-1 or a-2, it has to fix the second coordinate again. Like it can set it to any integer it wants, but it has to be finite. So again, if you like say changes the pair to a-1 a million, then the sequence has like only a million steps to go before it has to change this first coordinate again. So if the sequence starts with AB, then it has to repeat like a batches of steps, and each batch of steps has to be finite.
Exactly. Thanks. You can also see this in other way. So in order to show that this is quasi order, we can say, okay, let's take an infinite sequence of elements like that, and we would like to show that there is a domination. So by Dickson's lemma, we know that there is a domination of such a form, x, y, and then later some x prime y prime, which is which dominates the previous one in the coordinate-wise order. And you can see that this actually also implies that that one dominates the previous one in the lexicographic order. So this is another solution, which is of course harder to find, but but this is the power of lemmas which we already know, and this holds for any dimension. Okay, so it's already 5:15, so it's time to finish. So we will continue with the same exercise tomorrow at the beginning of our meeting. Okay, so thank you very much and see you tomorrow.